Okay, so in last lecture we started from angle and then went to angular velocity, angular momentum, and then finally torque, which causes a change in angular momentum. But as far as solving problems in this class, we're going to kind of go the opposite way. First, we're going to look at torque balancing problems, and then after we figure out torque, then we'll apply it to see how it creates changes in angular momentum, angular velocity, so on and so forth. So to start with, for looking at torque, we'll look at cases of static equilibrium. So that just means nothing is changing, or for most of these problems, nothing is moving or rotating at all, which means that our torques and our forces are both balanced. If our F net is 0, as we've learned before, that means that our delta P is 0. So if it starts at 0, it stays at 0. This is just that it is stationary, not moving up, down, left, right, in, out, anything like that. And then if our torque net is 0, that means that our angular momentum is constant. And if that starts at 0, it stays there. So it's not rotating, it doesn't start rotating, everything is balanced, which is exactly what we have in this picture here, where we have a person standing on some beam that's attached to a wall at a pivot, and then there's this rope that is holding it up. So everything balanced here, and what we're going to do is investigate the torque balance and the force balance and see what we can learn. So we'll assume this person has mass m, this bar, this plank has mass 2m, and that they're suspended by some rope with angle theta with the horizontal. And then finally, we'll say the plank has length length L, and the person is standing at the end of it, and that the rope is attached at 3/4 of the way down, so that this length from the hinge to where the rope is attached is 3/4. All right, so like we just said, we know that torques and forces have to add to 0. So in these problems, it's helpful to start with torque. So we know our tau net has to equal 0. Another way of saying this is that the sum of all the taus into the page is equal to the sum of all the taus out of the page, right? And this, from our perspective here, it would be clockwise or counterclockwise, but all the torques that want this plank to rotate down are balanced by the torques that want to rotate it upward. So let's go ahead and figure out what each of these things are, the sum of the torques into and out of the page. So let's start with into the page. So what is the sum of all our taus into the page? Well, if we want to figure out what the torques are, first we need to identify the forces that are at play here. So we have a couple things. The person is standing on this beam, so there's a force of gravity that's acting on the person and pushing down on the plank. So let's call that Fp for F person. We also have force of gravity acting on the plank itself. So this is kind of something that we just have to know, that gravity acts at the center of mass of things. So I'll just write that up here just so we know. Gravity acts at center of mass, or COM. So the center of mass of this plank is, well, just at its center. You can't really see that color, so let's make it a little, yeah. So we'll put the gravity arrow there. Oops. And I'm going to make that longer than the force from the person, which is also from gravity on the person, because we know that the plank is twice as heavy as the person, has twice as much mass. So this force is larger than this force, and it acts here. Finally, we have the tension from the rope. So this rope's attached to the wall, it's holding this plank up, and ropes can only pull along their direction. So this should be a straight line. It kind of came out curvy. But this we'll call tension. So I put it as T, but this is just a force. This is something we'll do a lot. It just helps when we're solving equations to not have so many F's floating around, but this tension is just the force that the rope applies to the plank. So what I've drawn here is called an extended force diagram. So let me write that here. Extended force diagram. And as the name suggests, it just is when you draw all the forces where they act. Before we drew forces all centered on one point. So we would have our object that's just a point, and then all the forces acting on it just condensed onto that one point. But now it's helpful to spread them out because we found out that for torques, it matters where the forces are, right? The radius, or the distance from the axis of rotation to the application of the force affects what torque will be created. So we do care about this. So we'll be going back and forth between these extended force diagrams and the other type, which I just drew, called a free body diagram. We'll do that for this example a little later on. But for now, let's stick with the torques. So the torques that are going into the page, if we use our right-hand rule, that will be the ones that want this to rotate from this perspective clockwise. So this is going to match torques into the page, right? So which forces are doing that? Well, it's the two forces from gravity, or gravity on the plank, and then the force from the person standing on the end. Both of these want to rotate the plank counterclockwise or apply a torque into the page. So what torques are created by these two forces? Well, we know torque is equal to F perpendicular times R, or also F R perpendicular, whichever is easier to find in a particular example. Both of these are already perpendicular to R, right? So we can draw that out. Our R is just, here's my axis of rotation, draw a vector from there to the force. So there's the one for gravity on the plank. There's the one for the person. And as we can see, these are right angles. The F's and the R's are already perpendicular. So for these two forces going to torques, we don't need to do any trig. So for gravity, it's just going to be Fg times its distance from the axis of rotation, which is L over 2, because if gravity acts at the center of mass and the length of this plank is L, then the center is just going to be at L over 2. So this distance here for this arrow is L over 2. So we'll have Fg times L over 2 for gravity, and then plus the force from the person, so that's Fp times its distance, and the person is standing at the end of the plank, which has length L, so that distance is just going to be L. So here's the sum of our torques into the page. We have the force of gravity acting at a distance L over 2 away, and the force of gravity on the person, or the force of the person, that is a distance L away from the hinge. We can go a little bit further. We know how to find the force of gravity here. Fg is just mg, and we know the mass of each of these things. So for the plank, the force of gravity, its mass is 2m, so this is going to be 2mg times L over 2. And the force of the person is also mg. Person's mass is just m, so this is going to be mg times L. These 2's cancel, so we just get mgl plus mgl, and our result here is 2mgl. So this is the total torque into the page. So if this is the total torque into the page, we know that also must be the total torque out of the page, because this system is in static equilibrium. It is not moving. So now let's do the same thing for the torques out of the page. Find an expression that's equal to that. So our torque out of the page, which we know is going to, in the end, equal to mgl. But what's providing that torque? Well, it's the tension, right? This rope is pulling up on the plank and keeping it from rotating down. The tension, however, is not perpendicular to R. So I'm going to erase some of this stuff so it's easier for us to see. but here's my R for the rope, right? We said that's 3/4 L. And the tension and this R vector here are separated by an angle theta, which is clearly not 90 degrees. They are not perpendicular. So I'll draw tension over here, just roughly. So here's our tension. And when I get rid of the vector sign, like I did for these forces and stuff, I'm just noting that that's the magnitude. So writing T like this is just the same as writing the magnitude of that tension vector, because this is the hypotenuse. So here's our tension, and then it has two components, a x component and a y component. The y component, or sorry, the x component here, this ty, the x component here is parallel to r, right? Here's our, if we put our r in this, our r would be going along this direction. So tx is t parallel, and for now, we don't care about that, right? Because it does not apply any torque, because it's directly along the position vector from where that force is. The piece we do care about, however, is this T perpendicular, the perpendicular piece of tension. Here's R along the bottom. Here's our T perpendicular that's directly, well, perpendicular to it. And so we care about this piece. And we also know that this angle here is theta. So we can use trig here. T perpendicular is opposite theta. So T perpendicular is going to be T sine theta. Right? So there's our F perpendicular. The tensional force is the force, and the perpendicular component we find from the sine theta. Great, so now we can plug that into our tension equation. Now our force is T sine theta, and its distance, like we said before, is 3/4 L, 3/4 L. Great, so now we have two expressions that are equal to each other. We know the tau going out of the page, or that wants to rotate this plank counterclockwise, is equal to the tau that wants to rotate it the other way. They balance out, and so these two expressions, as we've now written, are equal to mgl. The total torque going into the page is equal to T sine theta times 3/4 L. So this is our final torque balancing equation, or the result of our torque balancing equation. This is just when we solved this top thing here. So this turned into this when we evaluated it. I'll say we didn't really use any signs here. We could think about torques as like positive or negative, but I think it's much easier to just think about into and out of the page and keep everything positive. So then we can set one equal to the other. We know these are equal and opposite because we've said the direction of one is in and the direction of one is out. Again, I think it's when we did x and y, we kept track of what's positive x, what's negative x, and added them together. But as long as we always separate into the page and out of the page, we can keep everything positive and just set them equal to each other, knowing that these little vectors of into and out denote that they're going in opposite directions. Okay, so I didn't give us actual numbers for L, M, or anything like that, but let's say we were asked to find what the tension was in this rope or something. We could then just rearrange here, and if we rearrange this, the L's cancel, so we get, I think, 8 mg over 3 sine theta. I think that would be our tension. So, I didn't actually ask us a question about this one. We're just kind of investigating this in the greatest detail we can. But, this would maybe be the type of answer we would get if it asked us to find the tension in the rope. Maybe we were given the tension and want to know the mass of the person or the mass of the plank, something like that. Solving problems this is the meat of it, is figuring out how things relate to each other, and then at the end we can plug in and find the appropriate numbers based on what we're given, the unknowns. Okay, so now that we found the magnitude of the tension, that's the magnitude of this force right here, this tensional force. Let's go back and look at the force balancing. So we got all this from the torques, and we also know now that F net is also 0. Right, so the torques that all the forces make have to add up to 0. But these individual forces also have to add to 0 because, this whole thing isn't moving, right? This plank is stationary. So let's do what we're used to with balancing x and y components, except now there's maybe one more force we have to take into account. And we can see that because, let's make this free body force diagram. So I'll put that down here. That's when we collapse everything down to a point, right? So this point is our plank, which is the object that we were drawing all the forces on. So instead of making a long plank and putting all the forces where they apply, we'll just collapse them down to this one dot. And now we have our FG. We have our FP. Sorry, that's a terrible G. Let me fix that. We have our FP. This is the force of gravity and the force of the person, both acting downward. So I just drew them like this because we know they add up in that direction. And then we have this tensional force that's going up and to the left. So clearly we need another force because these can't add to 0, right? They don't add to 0. We do have some up component from the tension and some down component from the other two. So maybe in the y direction that could work. However, in the x direction, we have this negative x component from the tension, right? We have this piece of the tension, but there's nothing left to balance it out in the positive x direction. So we need another force. And where does that come from? Well, the hinge, right? This plank is also attached to the wall at this point here. It couldn't apply a torque, so we didn't consider it before, because it has an r of 0, right? It's at the axis of rotation, and you need some distance away from that to produce a torque, but it still can apply a force to this plank. So what direction does it need to be in? Is it pushing down, up, left, right? Well, we can use vector addition or subtraction to figure it out, because we know that all of these need to add to 0, right? So what's keeping us, so what's the difference between the sum of these and 0? Well, if I can rearrange these a little bit, I have my FG going down, my FP going down, so we'll just very quickly FG, FP, and then add on to that my tension. So I'm just rearranging this diagram here to do vector addition, and now to get from here back to 0, I must add a vector that looks like that. There's my F hinge that I'm missing. So we know, this isn't a numerical solution, but we know that F hinge must go up and to the right. And I guess the up part I kind of just assumed, but we didn't solve for what the vertical component of this is, right? What if this vector tension was much longer, right? What if it was something like that? Then to get back to 0, we would have this vector that goes a bit down and to the right. So we're not really sure about that yet, but let's do some math and see what's going to happen. But we know that whatever missing force we have has to be at least going to the right, because we have this unbalanced force to the left, or to the negative x direction. So let's write out our force balancing equations. In the x direction, F net x equals 0, and that equals the sum of all the forces in the x direction. So for x, Fg and Fp don't have any x components, right? Those are both straight down. So we just need the x component of the tension. We already did that. Well, not quite, but we did the setup with this little triangle diagram here. If t sine theta was the vertical component, the y component, then t cos theta, the adjacent side, is going to be our x component. So we have t cos theta for that, and that's going to be negative because it's going to the left, the negative x direction. And then we have to add on, so let me just add to our diagram here that hinge force. We don't know exactly its direction, but we know it has some positive x component, right? So we need the x component of that. So plus f h x. And let's go a step further. We know that fh is going to have two components, an x and a y. So let's do the work now and say this angle now here, we'll call that phi. Right, so we don't know what it is yet, but we will be able to find it. So that means that the two components of fh are going to be this opposite side here, the y component. That'll be fh sine phi. And let me zoom in a bit here. And the x component will be fh cos phi. So we can go ahead and plug that into the equation we've written with negative t cos theta plus fh, and that's going to be cos phi. Because of the angle we've decided is phi, fh cos phi. And yeah, those two sum to 0. All right, so now we know that fh cos phi is just equal to t cos theta. Right, all that's saying is that the x component of fh is equal and opposite the x component of the tension. Okay, now let's do f net y. So that's also equal to 0. And in the y direction, we have both force of gravity and the force of the person. And that's all of those, right? Because those are just in the y direction, so we don't need to do any trig. And then we also have the y component of this hinge force and the y component of the tension. Right? All four of these forces can have some component in the y direction. So let's go ahead and plug in what each of these things is equal to. Fg is the force of gravity on the plank. Its mass was 2m, so this is 2mg, and that's negative because it's pointing down. Force of the person's mass is just m, so that's just minus mg, right? Now the hinge force, well, let's do tension force first just because we already solved for that. We know the t perpendicular, the tension vertical component is t sine theta, right? T cos was the x, so t sine theta is the y, and that's going to be plus because it is pointing up, t sine theta. And then for fhx, or sorry, fhy, this is a little bit tricky because, like we said, we don't know whether it points up or down. But the way I've drawn it, it points up. So let's just assume it points up. And then when we solve, we'll see if it was negative, we'll get a negative number popping in somewhere that we didn't want it. So let's just leave it the way we've drawn it for now. So this will be plus fh. Y component is the sine theta, like we said. Or sorry, sine phi. Right, this angle here is phi. So now we can simplify this a little bit. We have minus 2mg minus mg, so that'll be minus 3mg. So we can move that to the other side, and we get 3mg equals t sine theta plus fh sine phi. So now we have this nice relationship. We also know what t is, right? That's what we solved. Well, one of the things we kind of solved for when we balanced the torques. We found out what the tension in the rope had to be in order for these torques to be balanced, which was 8 mg times 3 sine theta. So let's plug that in. So we have 3 mg equals 8 mg over 3 sine theta. That's our tension times sine theta plus FH sine phi. Here the sine theta, I drew a theta, that should be a phi. So the sine thetas here cancel, and we're just left with an 8/3 mg. So 3 mg equals 8/3 mg plus FH sine phi. And then we can move the 8/3 over here. So 3 is 9/3, right? So 9/3 minus 8/3, we'll just get 1/3 mg on this side equals FH sine phi. So now we solve for our x component up here of our hinge force and our y component of our hinge force down here. So the expressions that I have written out are very explicit, that the x is FH cos phi, the way we defined it, and the y component is FH sine phi. But another way to write this is that our hinge force is just a vector with an x and a y component. Its x component we found is t cos theta, and our y component is 1/3 mg. And I guess we do know what t is. We can plug that in a little bit more explicitly, just like we did up here. T is 8 mg over 3 sine theta, so if we wanted, we could plug that in. So now we have 8 mg cos theta over 3 sine theta. We didn't learn too much more there, but this is just to show that if we were given this mass and original angle of the tension, that would be enough to completely solve this problem. And also what we learned is that FH does point up and to the right. So both of these components are positive, right? So the information that mattered for that, I guess, was the breakdown in the mass, that the Planck was 2m and the person was m, and that gravity acts at L over 2, the person standing at L, rope is acting at 3/4 L. I'm just listing the setup of the problem, but essentially something in there was enough to determine that the hinge force also needs to have a positive y component, that the y component of this tensional force is not enough to completely balance these two. The thing that decided that was that the torques have to be balanced, right? So the torque that's produced by the y component of this tension force does perfectly balance Fg and Fp, but because of where they're all placed and the mass of each of these two objects, that balanced torque does not result in a balanced force, and we need an extra y component of the hinge force, which is this 1/3 mg, in order to balance both torques and forces. So now we started with this setup based on only the fact that this is at static equilibrium, there's no movement here. We were able to solve for the tension in the rope and the individual components if we wanted them, and the force from the hinge, the force coming from this piece here. Now we know it goes up and to the right. That allows the forces to be balanced, even though it does not provide a torque, right? Because the r is 0, the vector from the axis of rotation to the hinge is 0, because the hinge is where it rotates from. So there's a lot of information we can pull from this. Other takeaways from this problem, again, static equilibrium means tau net and F net are both 0. So these two small statements were the basis of all of these equations. For tau, we have an into the page and out of the page component to deal with and set these equal to each other. For f net, we have an x and a y component to deal with. We don't set those equal to each other, but each one of these is individually 0. And from that was our whole problem. Other pieces to remember, again, this is an extended force diagram. That's, as the name suggests, when we just take the forces and draw them where they are acting on an object. So this helps us calculate and visualize torque. And then down here, we have a free body, or a free body force diagram. And that's when we collapse the object down to a point and draw all the forces acting from that. And that is helpful for visualizing and calculating forces and force balance. The reason we don't need to extend everything here is just because, well, it doesn't matter where I apply a force, whether I apply it on the far left-hand side of an object or the far right-hand side. Pushing it up is going to make it go up. The rotation, it does matter where I push, but for forces, we can just collapse it all to one point. It does not matter. And both of these are helpful in their own ways. This helps us visualize the torques into and out of the page, whereas this diagram makes it much simpler to see that the y components of these balance the y components of these, and same for the x. That's hard to see when they're all at different places on the diagram. So I would get comfortable with any torque angular momentum problem drawing both of these. And that will be especially important when these do not equal 0. And we want to see where the net force is. So how is something changing its momentum, and when the net torque is not 0? So which direction is something going to have its angular momentum change? So for this problem, I didn't do much plugging in or real numbers. So I will also include a practice quiz solution in this little video makeup lecture series from one of the practice quizzes to get more hands-on practice.